Hi, everyone. This is Judy Warner. Welcome back to the OnTrack podcast. If you would, please subscribe and let us know what you'd like to hear more about here on OnTrack. Today, another amazing guest, Lee Ritchie, who truly needs no introduction, but if you haven't met Lee before, Lee is considered to be one of the industry's premier authorities on high-speed PCB and system design. He's the founder and president of Speeding Edge, an engineering consulting and training company. Some of you have read his book. He's author of Right the First Time. And he has a very illustrious, amazing background. And we also had the privilege of having Lee speak last year at Altium Live in Munich. So I'm delighted to have this conversation with Lee, not too long after DesignCon, so I know he'll have some great wisdom to share. So before Lee and I get started, also please connect with me on LinkedIn or on Twitter at Altium Judy, and Altium is also on LinkedIn, Twitter, and Facebook. Lee, I'm going to start with a very high-level question. First of all, welcome. It's good to see you again.
Thanks for the invite.
Always my pleasure. So you're known as the kind of a high-speed authority in our industry, but how did you get there? How did you be, out of all the paths you could have taken sort of in your technology field, how did you end up kind of going down this rabbit hole?
I started out as a microwave engineer on the Apollo program, which, as you probably know, is a long, long time ago. And the company I went to work for was in Silicon Valley when it was not yet Silicon Valley. Well, after we got through launching things to the moon, NASA decided, well, we're done with that, and lots of us, like 60,000 of us, had to go find something else to do.
Wow.
Well, I was in Silicon Valley, and the integrated circuits were starting to be a big play, and the big jobs were designing things with integrated circuits, digital, and so I interviewed for a job designing equipment for testing digital integrated circuits, and got the job and said, oh, now I got to go learn something about logic. So I went to bookstores and got books, and I faked it, and that's how it got my start. And of course, since I was already in the microwave end of things, transmission lines were already part of that, and that was what you had to be good at if you wanted to use ECL. And the high-speed computers back then were ECL. That's how I switched from microwave to what everybody calls digital. And for a long time, digital was slow enough that you could pretend it was digital, but I never did. And always designed with transmission lines. And so as the speed went up all around the industry, everybody needed to learn how to do something with this high-speed stuff. And I had a design company from 82 to 92 where we designed pretty much all the early boards for Sun, Silicon Graphics, Cray, people like that. And invariably I would get a new client, and the engineers knew nothing about high-speed design, so I'd spend 2 days teaching them the basics so that we could design their board, out of which grew the courses that I do now, which I first began to offer at UC Berkeley. And the complaint after every course was, there's no book, there's no textbook. And that's where the books that you came from, as I had to write those to make the students happy at UC Berkeley. And in 1999, we decided that we didn't like working for companies, so we started Speeding Edge.
Okay.
That's it. That's how I got here, almost by accident.
Well, I always say most of us got here by accident. I mean, some EEs take a nice, clean, straight path, but even they don't take that straight path. I know I didn't end up here on purpose either. But that's interesting. I didn't know that's how your book came to be. So the last time I saw you, you were actually speaking at DesignCon. And how often are you teaching these days, actually?
Most of my classes are private, and I would guess about every 2 months or so.
Okay.
They're 2-day and 3-day classes, so that's about as often as I want to do that. I don't know if you've lectured for 14 hours in a row, but it gets kind of wears you out.
I don't think I know anything about anything enough to talk for 14 hours. So maybe raising kids. I don't know. Like, I don't think I know about anything to talk that long. So now we know for sure you're way smarter than me.
Oh, I don't know. I just came from a different path. That's all.
Well, you and I were talking recently, preparing for this call, and we sort of went down this path talking about PCI Express. So can you kind of talk a little bit about the evolution of speed and the extremely acute curve that has been, sort of that we've taken in the last couple of years?
All right. Well, maybe I'll start with PCI itself, which is the bus architecture that has been in all the personal computers that you can buy. That's what PCI stands for, Personal Computer Interface. And it was a parallel bus that you might have 7 or 8 plug-in cards all on this bus that the CPU could talk to any of those anytime. And originally they was clocked at 33 megahertz, and it wasn't too long before the CPUs got faster than the bus, and all of a sudden we were what we call I/O bound. We couldn't get any more performance out of a PC because the bus was too slow. So we upped the speed to 66 megahertz, and then 100. And for a lot of reasons that are too complicated for today, we couldn't go past 100, and that limited how fast you could make a personal computer. And so we realized the architecture had to change. And the reason is that if the CPU can talk to any slot in the backplane at any time, to do that really fast, you have to have really, really short connections, and that was not realistic. So we turned to an architecture that actually is old. The differential signaling protocol that is in PCI Express has its origins way back with IBM. I was using it in '74, where we would connect 2 boxes to each other, where we couldn't do that with a parallel bus because the noise in the background was too high. And so this is not a new technique. It's just that early on, as you know, the guts of a computer is a parallel architecture, meaning lots of bits switching in parallel. And the differential links that we're talking about here are serial. So at each end, you had to go from a parallel bus to a serial stream on the line, the other end go back. And at that time, the serializer deserializers were extremely complex and expensive. So the only reason you'd ever do that is if you were stuck, you couldn't do it any other way. Well, as we've gotten to where we have 1 billion transistors in an IC, these serializers and deserializers are what we call basically free. So all of a sudden, it doesn't cost much to go from parallel to serial and back. And the advantage of that is you can drive. Well, let me stop for a minute. A parallel bus where either series or parallel terminated, if you're lucky, you can drive that at 2 gigabits per second. That's very hard to do. With a serial bus, we can drive them, and we are right now driving them at 32 gigabits per second, which you could never do any other way. And this is how we're getting all the performance we need in the internet and every place else, is with these serial links. And that's what PCI Express is. We switched from a parallel bus to a serial bus to allow us to go faster. Well, when you have serial links, you can only have a driver and a receiver on the same net. So how is it the CPU is going to talk to 6 or 7 devices like it was doing with the old parallel bus? And the answer is we have to have a switch chip somewhere so that we can switch between the CPU and whatever we want to talk to. Well, early on, those were expensive chips, so we only used PCI Express in real high-end PCs like a gamer would buy. Well, we've now integrated those switch circuits right in the CPU, so it's not an extra part to buy.
Oh, okay.
So it's everywhere. So pretty much everywhere we've got PCI Express. Well, in itself, it's not really all that big a deal because the early PCI Express was, well, it depends on your point of view, as fast as 500 megabits per second on a line, and that's not special in today's terms. The rub is we have started to go up the performance curve where we've got Gen 1, Gen 2, Gen 3, and so on. And Gen 3, which is just right around the corner for everybody, is 8 gigabits per second. And that's not slow. And we start to see things that we could ignore at lower rates. The one we're going to talk about today is not loss, it's the thing we call skew. Skew is the fact that the two sides of a differential pair don't arrive at the receiver at the same time.
Okay.
And I put some numbers on this. The most common, until recently, most common data rate in switches and routers for the internet was 10 gigabits per second, where 1 bit is 100 picoseconds. And I did a test board in 2013 at DesignCon where we discovered 62 picoseconds of error in a path,
wow,
which is almost an entire data bit at 10 gigabits per second, which destroys the link does not work. And of course, we got Gen 4 coming in at 16 gigabits and Gen 5 at 32, where 32 the bit period is only 30 picoseconds. So that error I just talked about is 2 whole bits. Well,
wow.
It means nothing's going to work.
Right.
So the question is, where did this skew come from?
So is that, Lee, let me interrupt you for just a moment. Sure. Is that what the course that you taught this year at DesignCon, was that your focus?
Yes, well, the course we talked about is a boot camp I call Getting to 32 Gigabits per Second, which covers a number of things, skew being one of them.
Okay.
Of course, the first worry most everybody had is loss. So we had this flurry of activity to make low-loss materials and smooth copper and on like that.
Right.
At the same time we were doing that, the IC manufacturers figured out a way to improve their circuits so that loss is not a player anymore. Not a big deal anymore. For example, the latest Vertex, I guess they're Vertex 8 or 9 from Xilinx, at 28 gigabits per second, the link can tolerate 38 dB of loss, meaning that we start out with, say, 1,000 millivolts, and we wind up with 4 at the receiver, and it still works.
Wow.
So all of a sudden, the drive to have the world's best lowest loss laminate is not a player anymore. Skew is.
Interesting.
Skew's killing everybody.
Oh.
All these laminates from people like Rogers, and you mentioned one earlier, I can't remember.
Taconic,
are simply not necessary. Not necessary. At any rate, skew is just, and that was the theme of DesignCon this year. It is, how do we control this bloody thing? So the question, I guess, that comes up next is, where's it come from?
Yeah. Where does it come from, Lee?
Well, if the two sides of a differential pair were different links, that would be, I think, obviously one way that can happen.
Right.
But pretty much everybody knows how to design physical links to a few mils. a few mils. So that tends not to be what the problem is. The problem is, and these are what we call micro defects or micro effects. The glass cloth in laminates, on average, has a pitch between threads of about 16 mils, between 16 and 20 mils. Traces are 4 or 5 mils wide. So there's a huge difference between the width of a trace and the spacing of those glass fibers.
Right.
Well, laminate is a mixture of glass and resin. And the dielectric constant of glass is on around 6. And the dielectric constant of resins is less than 3. That means that, I mean, the lower the dielectric constant, the faster the signal is going to go through the material.
Right.
So if I had one side of a differential pair on a glass bundle and the other one in between, there are 2 different speeds. That's where the problem comes from.
Now, along those lines, I was just talking to Chris Hunrath from Inselectro, and he was talking about spread glass. What do you think?
That's what the answer is.
It is? Okay, because I've been here at Altium a little over a year, and I guess I missed the spread glass thing, but I'm like, that actually sounds like it makes sense.
Well, I and my colleagues have been the drivers of spread glass.
Really? Tell us about that.
Well, so we found, I got to confess, we found out by accident.
That's how all good inventions are found out, right?
And it had to do with, we were, let me think about when that was, about 2005, we were trying to improve the uniform distribution of glass by using 2 plies of thin glass, hoping that they would sort of average out. And I had a fabricator in Oregon who says, if you use a single ply of 3313, you could save some money. So we built a test board. And by chance, that was really spread very nicely. And so we had no skew problems. So all of a sudden we thought we've solved all the world's problems by just using this glass. And then we built our test board from a different weaver.
Sorry, didn't mean to laugh, but I come from the board industry, and it makes me, yeah.
So, and this weaver spread the glass in one direction, but not the other.
Yeah.
So if you were to get that design con paper, you'd discover that we had really good skew one way.
One direction.
And so back to square one. Why are people spreading glass? So I got to digging around, and it was for laser drilling of blind vias.
Exactly.
Because if you think about it, if you have like the classic 4 mil core was stuff called 1080 glass. If you look at that, it has the glass bundles are round and not spread out. There's big voids in between.
Yeah.
So if the guy drilling the laser drill blind via wanted to get rid of the glass, he'd set the intensity to burn the glass and then go tear right through the backstop where the resin is.
Exactly, right.
And so the laser drilling industry is the one responsible for spreading glass.
Like you said, complete accident, but...
It is. And they don't care about signal integrity. They care about laser drilling.
Right.
So I and a guy named Scott Henniga of Cisco started going to IPC's sessions on standards for glass weave, with the intention of getting some standard for how you spread the glass. Well, it was a whole lot like herding cats.
What, an IPC committee being like herding cats? I don't know what you're talking about, Lee.
Yeah. Well, so around the table we had 5 or 6 weavers, and they would not tell us how they wove their glass.
Because it was proprietary?
Yeah, so we couldn't come up with a standard. And the only standard that the laser drilling people had was you take a section of this cloth and they put it in the chamber and see how put compressed air on one side and see how leaky it was. That's it. That's all there is today. If it was leaky, less leaky than X, it was good.
Oh,
well, that's not be good enough for what we're doing here.
Yeah.
So we are not done solving this problem. And there's about 7 or 8 different ways that people approach it. If you were at DesignCon this year, you discovered 2 papers were presented by Cisco where when they built the boards at 5 degrees to the weave, they got the best skew results. So that's how they're solving it.
Yeah. Can
you imagine what that happens to you at a fab shop if you say, cock this artwork on the lamp panel at 5 degrees?
Well, I remember hearing about from a colleague who was in the EE, they were actually at some point, because of the glass crossing and there being those bundles, they were actually starting to do it at, basically lay the pre-preg at a diagonal. You follow what I'm saying?
Oh, yes.
You remember that? That was kind of going on for a while to see if that would help. And I think it did help a little bit. But again, the expense, there was so much loss of materials doing that it didn't make sense. Or there was the trend of making that weave super, super tight. So at least it was consistent, even if it was lossy. So I feel like we've been going at this a lot of angles. But hearing from Chris Conrad at Inselectro, it sounds like some people are really moving towards that spread glass and getting some good results.
Oh, that's my choice. But if you were to get the PCI Express design guide from Intel, they would tell you do one of 2 things. You route all the signals at 15 degrees through the X and Y axis, or you route them X and Y, and then you have the fabricator rotate the artwork 15 degrees on the panel.
Yeah.
That's in the standard for PCI Express.
I had no idea that was in the standard. And I'd heard of it happening kind of anecdotally, but I didn't know it was actually written into standard.
It's in the standard from Intel. And you can, if you imagine a backplane where you have a regular array of pins for connectors and so forth, there is no way to route it at 15-degree angle because it's constrained by the pin array that's X and Y.
Right. Yeah.
So that's not a choice. So that leaves you with only the choice of popping the thing at an angle on the panel. And you've been around enough to know the fab shop's going to look at you like you've lost your mind.
Yeah.
Well, we're not doing that. We've found some weaves that we know are well enough controlled that we're
good.
Succeeding without that.
Okay, good. That's good news. So the spread glass that's helping with the skew, you're saying, along with other things.
It solves the problem.
It does.
Yeah.
That's amazing.
The rub is you've got to be very careful who the weaver is.
Well, can't you spec in a certain...
I started telling you that I had 2 weavers of the same stuff. That's the problem when you say 3313. There's no standard. That just means there's X threads in this direction and Y in that direction. That's all it means.
Are there pre-preg providers that are... It sounds like there's pre-preg providers that are doing the way that you prefer, or maybe other high-speed...
There are.
So do tell, or can you tell?
Well, the Doosan material I mentioned to you before we started this is one of those.
Okay.
And a couple of isola materials are in that, and nothing else is.
Okay. Well, that's a good hint. It's a good hint.
Everybody
knows where to look. I mean, I'm doing this podcast hoping to be like have takeaways, so I don't just bring up all the problems and then say have a nice day.
Well,
So thank you
that's
for
true.
sharing that. Right, that's the goal. Like,
Yeah.
yeah, I found out what works. Good luck. No. Um, so I have been seeing this word and this thing skew. So thanks for sharing that. One thing I could see as a potential problem, and tell me if I'm right or not. Since that speed curve has risen so acutely, it seems like kind of the people who weren't previously doing high speed design must be getting pulled into that space, whether they want to go there or not, right?
Yeah.
Is
Yeah.
that, would that be a correct statement? So
That's true. Yes.
you and I were talking before this call about, let's talk about resources, about where these designers that are coming into this space. I mean, speak just a moment about DesignCon, because I know you're pretty passionate about that show, in particular, giving out really good information.
Well, DesignCon is the only conference I know where the level of information you need in this area exists. It's where everyone who has done research or has studies and that sort of thing that are advancing the state of the art, that's where the papers get presented. It used to be that was it. That was it. There was no tutorials, no education, that sort of thing. But over the last 4 or 5 years, we've added several things. This year we had 3 all-day boot camps on topics that matter to people who are trying to get on top of things. I did one titled Getting to 32 Gigabits per Second, which dealt with all these topics. Intel did a 3-hour on what is this PCI Express and what do you have to worry about, for people who have not seen it before.
Yeah.
And if it was 5 years ago, I'd say there was nothing there for a board designer. Now I would say it's the place you go for a board designer. There was a time when PCB West was, but that is not offering. I've been keeping track of that for quite a while. Not offering the kinds of things you need for these topics, and I'm not sure why. I certainly have been talking to the people who run it, saying that you got to offer tutorials. It used to do that. We used to offer stuff for engineers, and they quit doing that because, well, the guy who was running it was a board designer, and he considered board design an art, and dropped the stuff that appealed to engineers. Well, now that stuff has to be learned by the designers.
It does. And as an old board designer person, I had to learn it from the board manufacturing side, because I didn't realize, because I had left the industry for a while and come back, that things have sped up so much that board designers all of a sudden weren't just dealing with, oh, here's the specs, just adhere to the tolerances, do what the documentation says, and have a nice day. There wasn't, like, now high-speed board designers have to think about performance and all this wacky stuff. I mean, the way we clean the board, the way we etch the board, the way we drill the board, everything can, in a positive or negative way, affect the performance. And it mortified me to think we got to a space where we could be completely IPC compliant and the board wouldn't perform as expected.
Yeah, so that's a good thing to observe, and that is standards. By definition, standards document the past. By definition, and there are no standards group I can think of right now that is more behind the curve than IPC is. Because
why do you think that is? I have my suspicions, or I don't know that you're probably right, actually, and you're more of an authority than me, but I'm just wondering what's caused that to happen?
Well, who's driving it?
Mm.
Who's driving it? Well, volunteers are driving it.
Mm.
Where do they come from? Well, when IPC was at its prime, the standards committees were all staffed by engineers from aerospace companies.
Yeah, true.
And the quality of the work was superb.
It's very true.
That's not true anymore. Not true anymore. Who goes to IPC now? I don't. Nothing there for me.
Why do you think the committees aren't run by aerospace engineers anymore, or the Intels of the world, or Cisco's? Why do you think it's not?
I wish I knew.
Yeah, I really don't know either. I thought maybe you'd have some.
Well, in the aerospace, that part of it, the aerospace contractors got out of the standards business. And remember Jimmy Carter had a thing, the commercial off the shelf, fastest, but at any rate, we're going to...
Yeah, faster, cheaper.
Yes, and the standards bodies that the aerospace had lost their money. For example...
so they lost their funding to focus on that kind of thing.
110C, you've probably heard of that.
Mm-hmm.
You know the last time it was updated? 1998.
How outdated do you think that is?
And the update was to correct some spelling.
Oh my gosh, that's just plain sad. But they've come out with AS 9100 and other things to replace it. I don't know the quality of those specs, but...
Well, aerospace is on average about 15 years behind industry now. It used to be the other way around.
Yeah, it's just really sad, but I think that speaks to a lot of the way that politics have been run, unfortunately, and the way things are getting funded.
Yes, yeah. Aerospace doesn't drive technology anymore.
Yeah, that's a crazy thing to say out loud. I don't know, for you and I have been around a little while. So before we get too far off track, so DesignCon is definitely one place. Now, because DesignCon, if you pay to go to DesignCon, you can get all the proceedings. What can you do if you didn't go to DesignCon?
Well, you can for $100 buy all the proceedings for a given year.
So someone could go on their website right now and for $100 buy.
All the papers are presented this year, correct?
That's amazing. Okay, well, that's a really good resource. Obviously, your book, which, because we're going to talk, I went on your website and I noticed you're having some kind of fire sale on I don't know if it's part 1 or something, but right the first time, it looked like you were selling it, and then it sounds like you now have a digital library of things you've published over the years.
Well, that's true. And back on the topic of the books, we have 2 volumes, and there was originally going to be 1, but I don't know if you've written books or not, but you start out with great enthusiasm with this long list of topics. Mm-hmm. And I had a deadline, which was a Berkeley class, and I was only halfway through my list. And so I said, okay, this is volume 1. Next year we'll do volume 2. And what you probably don't know is our books are printed in color. because I
Oh.
think you have to have that in order to illustrate a lot of the things that matter. No technical publisher will publish in color. None of them.
Really? I didn't know
Nope.
about that. I know it's expensive, but I didn't know that
So,
they wouldn't do it
so
in
we,
color.
yeah, so we
Oh.
self-published.
Oh.
We formed our own publishing company, and we went to a printer and said we want to print this book. And here's a little secret about publishing.
Bonus material.
You have to give them a check for all the books before they turn the press on.
Oh boy, that's expensive.
So for each of these 2 volumes, I had to write a check for $50,000
Wow.
and
Ouch.
cross my fingers that someone would buy them. Otherwise, my garage would be full of books. Well, we sold out of volume 1, and when volume 2 came along, it sold faster than volume 1 did because it was a pull from volume 1.
Right.
I have this debate: do I want to write another check for like $50,000 to get to print more volume 1s? And the answer is no. So it became an ebook.
Oh, okay.
So if you go on the website, when you buy, you get them both. One's an ebook and the other is a hard copy.
Okay. Smart.
And 200 books from now, they'll both be ebooks.
You got smarter.
My garage will be empty. But I thought it essential that the book be in color.
That makes sense because some of those diagrams you can't distinguish between certain things without color being present.
No, think about all the curves you try to illustrate.
Right.
And so we are publishers, and we sell our own books. And people say I need to write volume 3, and there needs to be a volume 3 to cover the things you and I just talked about.
Mm-hmm.
But I have told my friends, if I start talking about writing another book, their job is to slap me around until I get over the idea.
Well, I'm not going to slap you because the speed curve's going ahead. Now we need to learn about skew and stuff. So,
But
and who else? Lee Ritchie is going to write that book. Like,
I
that's
have actually written another book in the form of newsletters and articles that are on that
yeah.
CD. And someone should put them together, but it's not me.
You know, you should get our friend Barry Matties to do that for you. Maybe he will.
You saw my distraction behind me, which is the model railroad, and that's more important.
Okay, well, I'm going to ask you about that. So I'm putting a hold on that subject. But let's cover a couple more quick things. One, you and I had an interesting conversation about circuit board manufacturers that are capable of doing good high-speed work. And I made a comment, and you corrected me right away because I said, well, board manufacturing hasn't changed that much in North America over blah, blah, blah. And you said, no, that's not true. And I said, except for places like TTM. And you said, which TTM?
Yes.
So tell me what you meant by that and fill our listeners in, of that conversation you and I had, because I thought it was very valuable, actually.
Well, when you say TTM, you're really talking about a dozen or so fab shops, which were acquired one by one, and they all have different capabilities for different markets. And if you're not careful and you get a bid from say TTM, they'll choose the fab shop that has the most capacity at the moment,
right?
Which may not have the skills you need.
Mm-hmm.
And so I learned the hard way. You have to know what their capabilities are, and when you give the order, you say what plant is allowed to build the board.
And they'll accept that request and send it to which location?
They won't get my business if they don't. It's very simple. I've got the check.
I am writing the check. You will send it here. Yeah.
Yes. And if you don't do that, you won't get paid.
Yeah. That totally makes sense. Well, you and I talked about Stafford Springs, which is a board shop, one of TTM's facilities I've always wanted to be through, and it sounds like you've been through, and that sounds like at least one of the locations that is capable of doing those high-speed designs.
That's right. And another one is in, I want to say Hillsboro, Oregon.
Okay.
It was originally called Merrick's.
Oh, yeah, I remember Merrick's.
Yeah. And of course, if I'm building small volumes, it's my choice is a little place down in Orange called MEI.
It's not MEI anymore.
No, it's got another name.
It's Summit Technologies, which I agree. They, I know Jerry Partita there. Hope to have him on this podcast, actually, because I think they've done a real good job there.
Yeah. So you're sort of touching on something that we ought to say explicitly. If you're designing for this kind of space, you need to be in direct conversation with the engineer at the fab shop.
Yes.
So that you don't make decisions that are not realistic. And
So
I always have got that guy at the other end when I'm designing a new board.
I think
Always.
that comes up again and again on this podcast, by the way, people saying you have to talk to the key people at the board house, which I totally agree with. So let's talk about, I used to blog on Microwave Journal about which shops I thought, because I was working for Transline Technology, which is a really small board house in Orange County, but they're very quite good at RF and microwave. But I used to try, because I would see board houses say, sure, yeah, we do high speed or RF and microwave, because they've been built on, say, Rogers 4350, which processes much like FR4.
Not really.
But, well, not exactly, but close. It's pretty stable. But then they would take an order for something that was PTFE because they'd built some 4350. I'm like, and then they'd fail and say, sorry, we tried to build it 3 times and we failed. And I kept seeing this happen over and over again. So I started writing about what I thought people should know, what they should look for in a good board manufacturer, i.e., what percentage of their work is high speed.
So let's stop for just a second and clarify what high speed means.
Okay.
Because RF and microwave is
certain
not
speed.
high speed with respect to digital world.
Yes, that's true.
Actually, RF and microwave boards are simple compared to digital boards.
This is true. Yes, that's true. Then high speed digital.
I actually consider them to be trivial.
Yeah, but some of the stuff you do on those RF and microwave boards are funky and weird.
That's not because they need to be like that. That's because RF engineers say things that are goofy.
This is true.
It's
true. No, it is true. Because, again, why I started blogging is because RF engineers were starting to lay out their own boards, which was not a good model.
Yeah. But remember, I'm an RF engineer.
Yeah. But you're...
And so most of the stuff you see people asking for on those RF and microwave boards is goofy. It's not good engineering, pure and simple.
Yeah.
At any rate, so when we're talking about high speed, I'm talking about, because this is far and away the majority of it, things that are high speed digital.
Yes, high speed digital. Yeah.
Yeah. And the people who can do that are good at laminating high layer count boards.
Mm-hmm.
And very rarely is an RF or microwave board high layer count.
Nope.
Almost never. Yeah.
Yep. This is true.
Yeah, two different
It is
animals.
2 different animals.
So if a guy says I'm a high speed fabricator and I make RF microwave boards, that's a different capability than what I need.
Yes, it's true. So let's just talk about high speed digital. So you're right. Somebody who can do high layer counts. What would you look for, laundry list wise?
Well, at the top of the list is boards like mine. if you're not making boards like mine, you're going to learn on me, and I'm not ready for that.
Yeah, that's a good point.
Yeah. I mean, it really is. That's my first thing. Are you making boards of the same class that I want you to build? If the answer is no, I'm going to go someplace else.
And I would say, and how much of their work is like your work? Because if it's a really small percentage, that would make me nervous too.
Yeah. Well, it's my experience that if somebody's making highly current boards, that's about all they're making.
Yeah,
that's about all they're making.
It's true. They kind of aim at that. Mm-hmm.
And if they're good at it, they're busy.
Yeah, and they're busy, and right, and that's what makes them profitable, actually. So,
yeah.
And that also you will see the equipment set that goes.
There you go. Exactly.
You won't see archaic. You'll see the most modern tools that gives them the precision and.
Yep, exactly.
Mm-hmm.
And really good vacuum lamination.
Mm-hmm.
And superb plating.
Yeah.
I mean, a guy can plate a 4-layer microwave board will fill at a 24-layer board with 10 mil vias and 12-to-1 aspect ratios.
Yeah.
And so you got to go find fabricators who are in your sweet spot.
Yeah, I agree with that.
And and of course, if you're at it for a little while, you figure out there's about 6 choices in the U.S.
Yeah, it's true. There's not a lot.
Mm-hmm.
And as you're speaking, those are coming to mind.
Yeah.
I won't sell for anybody today, but they are relatively easy to find.
And now, just before we finish that,
okay.
10 years ago, there were none in Asia because they were busy making consumer electronics.
Yeah, I'm interested in your perspective on that because I don't really know what that is. There was none if it wasn't kind of cookie cutter consumer. So what's the state of the ability in China these days?
We've got as good a capability in Korea and China as there is in the U.S.
I guess that's good news from a price point standpoint.
Yeah, and it's bad news for the American laminators, though.
I know. It's which, I'm an American and I feel whatever, but it is what it is.
Don't forget, wasn't so long ago, we made TVs.
I know. We made a lot of stuff.
It's the nature of business that we go where the low-cost labor is.
Yes, it's true. Okay, now back to your trains. So always at the end of the podcast here, which we are beginning to wrap up here, and thank you so much for your time. I always learn a lot from you, Lee. You are working on this part of the podcast I call Designers After Hours, because my observation has been a lot of people that I know that are pretty smart engineers and designers have neat hobbies after hours. So tell us about your after hours fun.
Well, the one that you can see in the background is a model railroad.
Let's see it. Can you flip your screen that way without disrupting us? Oh, there it is.
Can you see it?
Yep, I sure can.
And the one you can't see is I repair vacuum tube radios.
You do what?
Old radios, vacuum tube radios.
No way.
Yeah.
Just for fun?
Yeah.
Who still uses vacuum tube radios?
Well, we're starting to get hi-fi guys who think that vacuum tubes are the way to go. But I started out spending money as a kid fixing radios.
Oh.
See, I've always been a nerd. You just may not.
Yeah, I know.
but so I'm just back to fixing old radios.
That's kind of a fun hobby. But vacuum tubes, that cracks me up.
Yeah. You probably didn't know you can buy new vacuum tubes.
I didn't. I didn't, but I was talking to someone recently and it cracked me up because I remember doing this as a kid. So remember going to like the drugstore, the hardware store, and you could test the vacuum tubes
Yeah.
in the machine?
Come on over. I've got a tester.
No way. Somebody
Yeah.
mentioned that. And I was like, whoa, like my childhood came flooding back, going with my dad to the store and sticking in the vacuum tube testers. That's funny.
Yeah.
Good times, good times. Well, we're about out of time, Lee, so thank you again for your time. And I know we could go further and further, but I will share the link to your information about your books, and I will also share the link you shared with me for the design con so people could download white papers. And if you think of anything else, just let me know and we'll put it on the show notes here so we don't leave people feeling hopeless. We get them registered for design con and get some papers in their hand and get some books in their hands so they can do their job better.
One last thing we talked about, I ought to mention, if you do those, what do you call the thing we did in Munich?
Oh, Altium Live.
Oh, yeah. If you keep doing those, I would argue you should start offering these training courses.
Okay. All right. You heard it here from the mouth of Lee Ritchie. I have to go show this to the CEO later. Prove.
Okay.
Yeah.
Been my pleasure.
Thanks so much, Lee, and we will talk to you soon. Again, this has been Judy Warner with the OnTrack podcast. Thank you for joining us, and thank you, Lee Ritchie. Have a good day.
Have a good day. Bye-bye.
Bye.